Hello! Welcome to the part 2 of our Introduction to Operations Research lecture. Here, we will be talking about linear programming, or LP. We will talk about its different elements, and then we will solve or model one problem in order to fully understand how to build an LP model. So let's begin. What is linear programming, or LP? Linear programming calls for optimizing, either maximizing or minimizing, a linear function of variables called the objective function, and it is subject to a set of linear inequalities and/or equalities called the constraints. Now let's break down each of the elements. First, we have decision variables. Decision variables are the unknowns which are to be determined from the solution of the model. One common example is the number of products to produce. Then we have the objective function, which is the linear function that we want to optimize. Again, either maximization or minimization. For example, maximize a profit or we minimize cost. And then we have the set of the constraints, which limits the decision variables to their feasible values, or if you are going to graph them, the feasible region. The most common example for this would be raw material availability and production hours. And then lastly, parameters. Parameters, or a parameter, is a numerical factor that defines a system. For example, the selling price, or profit, or consumption rate. The best way to understand how to make an LP model is through an example. So let's try. Let's say, for example, we know Bob the Builder. And Bob the Builder wanted to create two products, a table and a chair. Bob the Builder's question now is, how many products should be produced to gain maximum profit? So let's try to help Bob the Builder create an LP model. Remember that an LP model consists of decision variables, objective function, constraints, and the parameters. So first, what we have to do is to let variables x1 and x2 be the number of tables to be produced and the number of chairs to be produced, respectively. The x1 and x2 will now be called our decision variables. Every time that Bob will produce a table and a chair, he will receive a profit of $2 per table and $5 per chair, for a total of the variable z, which is our total profit. And if we're going to multiply 2 and 5 by our decision variables x1 and x2, this will provide us with our total profit. And what we want is to maximize this. This is our objective function. And then, of course, we have the limitations of the system. First is on the number of machine hours. In order to produce a table, Bob needs 3 hours on the machine and 4 hours for creating a chair. And Bob only has 200 hours of machine hours. So basically, in order to create the total number of tables and chairs that he needs, it must only be less than or equal to 200 hours. Then we have the units of raw materials. So for every table, Bob would need 9 units of wood, and for every chair, he needs 7 units of wood. And the total available units of wood is only 300 units. So this is another constraint, where if we're going to multiply it with our x1 and x2 and get the sum of both, it should be less than or equal to 300 units. So basically, the total number of units that Bob should be able to use to create tables and chairs must be less than or equal to 300 units. And lastly, we have the minimum requirements. Bob needs to produce at least 20 products of tables, but there is no minimum requirement of creating a chair. This is again another constraint, where x1 should be greater than or equal to 20 because he needs a minimum requirement of 20 products, and x2 be greater than or equal to 0 because he may have the choice to have it 0 or even more than that, but not less than 0 or negative chairs. All of these in our table are called our parameters, or the limiting specifications of our systems. Now let's put them all together. First, we have our x1 and x2, which is again the number of tables and chairs to be produced as our decision variables. Then we have our objective function, which is to maximize our profit z, which is equal to 2x sub 1 and 5x plus 5x sub 2, which is subject to our set of constraints, which is the first one is the number of machine hours constraint. Then we have our units of raw materials constraint, and then our minimum requirement constraints, which is also called our non-negativity constraints. There are three different main properties of an LP model. First is that the objective function and the constraints are linear expressions of the variables. So these are functions of our variables. Then we have our second property, which states that each constraint may be of type less than or equal, greater than or equal, or equal. And then lastly, that all variables of the LP model are non-negative. It's because we deal with real-life problems. From our problem with Bob earlier, we cannot produce negative chairs or we cannot produce negative tables. So it should at least be x1 and x2 be greater than or equal to 0 or even more. These are again called our non-negativity constraints. This is how our general linear programming model looks like. It should have an objective function, which is we're going to minimize or to maximize, and it should be subject to different constraints. But there are problems which are really wide. Let's say, for example, our number of variables is 100, and then our number of constraints is 1,000. If we're going to write it in this general LP model explicit form, it would be too much and too big. Thus, we have what we call the general LP model compact form, where we use mathematical techniques or mathematical expressions like the summation or the for all signs in order to make our explicit form really compact. This is the comparison between the two. If you can observe, the number of our constraints is only limited to two. One is our set of constraints, which is the limiting specifications, and then our non-negativity constraints for our compact form. But on our explicit form, there are really a lot. To learn more about LP modeling, I have put here two different homeworks. One is where you formulate the problem as an LP model, and the other one is to transform the LP model to its compact form. Thank you very much for listening, and tune in for part 3 of our Introduction to Operations Research. This is Bontley for DC Cornelia, and have a great day.